Hello, good evening. Can you hear me?
Yes, sir. Good evening, sir.
Wait for some more time, let others join, then we will start formally.
Okay, sir. Sir, I have some doubt. Can I ask now, or
Uh,
shall we, shall I wait?
okay, you can ask. Go ahead.
Sir, actually, my doubt is not on non DC-DC. That is on linear regulators. Can I ask it now?
Okay.
Sir, in the linear regulators, in the shunt regulator,
Hmm.
mm, sir, while selecting the output load, the resistance that we can connect,
Hmm.
sir, what we are doing is actually we are removing the zener and then keeping the source voltage at Vmin. We are calculating the yes, sir.
Okay. Go ahead.
Yes, sir, this is RS, and so for calculating this RL,
Hmm.
uh, uh, we are considering the source to be of Vmin. That is okay. We consider this. We take Vmin is having at that time. We are calculating RL. That I can understand, sir. Why we are calculating RL at Vmin, sir. But while calculating this RL, we are removing this zener, so that through RS only I min is flowing. I min is flowing through RS. Uh, so for
You
that,
do not calculate RL, right? Or are you talking about some maximum
yes,
or
sir.
minimum value of RL?
Yes, sir. That is what. Yes, sir.
What?
That maximum RL that we can connect here,
Huh.
sir. In that, we for I min current flowing from the source, we are calculating the RL by removing zener.
By removing Zener,
Yes, sir. That is the way they are calculating in the videos.
like this.
By removing, yes, sir. By removing zener, they allow all the current I mean from the source to flow through the RL, and for that current they calculate RL. They find RL.
Which value of RL? Minimum or maximum?
Uh, maximum RL, maximum RL that we can connect here. Sir, in that case,
Hmm.
if we connect the same RL here, suppose we are calculating some value of RL through that procedure, and
Hmm.
if we connect the same value of RL here with the zener, so it will this zener will draw definitely some current out of this I mean some value of current will flow through the
I'm
zener.
not exactly able to understand the problem. So let us uh, say the Zener voltage is Vz.
Yes, sir.
Okay. So what we have is VL equals Vz. So
Yes, sir.
the source current is Vin minus Vz by Rs plus,
Yes.
no, not plus. This is the source current, right?
Yes, sir.
The source current. Now, what is the load current? Load current is Vz by
RL.
RL. So
Yes, sir.
your diode current comes out to be Is minus IL.
Mm. Yes, sir.
No, sorry, not like this. Is minus IL.
Yes, sir.
So what you have is smaller say you are saying maximum RL. So if I increase RL, that means I'm reducing the load. IL will
Yes, sir.
drop. I will drop. Okay.
So, sir, just a minute, sir. Uh, sir, this RL to reduce, sir. If you
You are
reduce RL,
saying maximum. Okay, whatever. Then if I reduce RL means I'm increasing the load.
yes, sir.
That means I'm increasing IL. Now,
Yes,
if I assume that the Zener holds this voltage Vz, whatever might happen, then Is is constant, right?
yes, sir.
This thing is constant.
Yes, sir.
So increasing IL means
Uh,
reducing ID,
yes, sir.
reducing ID. So if I now look at the current versus voltage of Zener, it is like this, right?
Yes, sir. Ideal Zener.
This X is voltage. Voltage is constant for any value of current. Now the thing is that this is
Yes.
the minimum current.
Yes, sir.
You cannot. So what is happening is, with increasing the load, the
Uh,
diode current is reducing.
yes, sir.
So we are moving towards this
I
side.
mean, yes, sir. We are
Yes.
moving
So
towards
there
I
is a
mean.
limit. So there is a limit on how much. What is the maximum load that you can have? Where from
Yes, sir.
we can get that is from this value of I mean whatever you have from the data sheet.
Yeah.
From
So
the
there is a limit on the minimum RL that we can connect.
yes.
Sir, yeah. There is, yes, sir. For calculating this RL,
Hmm.
uh, they are assuming the current is coming from here to the IS. They allow all the IS to flow through RL. That is this IS. They are taking this source. Source is fluctuating between Vmax and Vmin. They are calculating this RL at when the source voltage is at Vmin. Uh, so because that is where regulation will be maintained even at the least RL, the regulation across the Zener will be maintained so that they are taking Vmin. So if Vmin is at the source, then the source current flowing through RS is also I in min.
All I can say
V in
is that the minimum value of V in, sorry,
uh,
minimum value of V in that must be greater than Vz.
yes, sir. Yeah, that
Okay,
is correct, sir.
but why are they saying at that time? What does it mean? No diode.
Yes, sir, that is my doubt actually. They calculate RL by assuming current flowing through RS equal to current flowing through RL, and they are saying that is the least resistance that
Okay,
can be
wait,
connected.
wait, wait. Let me
But
think a bit. Okay, so I think that thought came from here that as we reducing the RL, that means as we are increasing the load, my diode current is reducing. Okay,
reducing.
so
Yes, sir.
maybe if we think about even more idealized uh, diode characteristic, Zener characteristic should be like this, right?
Yes, sir.
If I draw it once again here, like a rectangle coming vertically down,
Yes, sir.
right? So increasing load means my diode current is going here and it becomes zero. So diode current zero means no diode.
Yes, sir.
So that, so what if we have no diode? So basically, if you want a constant regulation at this condition also, then your load voltage VL should be equals to Vz, which should be RL times V in by RS by RL. Okay.
Okay, sir.
So
Okay,
if
sir.
this thing happens, that means V in mean. Okay. So this means even at the minimum value of the input voltage, my output voltage is held constant at Vz.
Yes,
From
sir.
here you can calculate your RL. Now if it so happens that you increase RL, if you increase RL means voltage across RL increases, that means the diode again comes into action because it will not allow something more than Vz across it.
Yes, sir.
Is it clear?
Yes, sir.
So if you calculate RL from here, from some so whatever, okay, let me write what you get. Sorry. So what you get is okay, RL is there also. Okay, whatever, you get RL, which is a function of RS and V in minimum. Okay.
Yes, sir.
Now you put your RL like this. So if you put your RL like this, what is happening is at the minimum source voltage, the load voltage equals the Zener breakdown voltage. If I write it as say VZB, then the load voltage equals the Zener breakdown voltage. So the Zener is not working at that time. Okay, there is no current through the Zener. Now what is happening is whatever voltage we are getting across RL, that is being determined by this equation, just by the voltage division law, right? Now if anything changes, now suppose if you reduce the load, means if you increase the value of RL, so by voltage division law, RL tends to get more voltage across it, VL tends to increase, right? So VL tends to increase means the Zener now comes into action and it clips the voltage.
Okay, sir.
That is how it works. So I think that is what they're trying to say.
Yeah, sir. That is okay, sir. But sir, the thing is, sir, they are calculating this minimum value of RL by removing this Zener. But
I know.
once they connect this RL back, definitely the current flowing here will be less than without Zener. So at that time, the resistance that can be connected here goes up. The resistance that can be connected across the load to
I
have
don't understand your
regulation.
question. You are saying that they are connecting the maximum load, right? The minimum RL.
Yes, sir.
We
They
established
want to
that.
calculate. They want to
Wait.
calculate minimum RL that can
Wait.
be connected.
We established that with reducing RL, the Zener current reduces,
Yes, sir.
right? So from this graph, we established that so there should be a minimum value of RL. There is a limit on the maximum load,
Yes,
right?
sir.
Now we are trying to
Yes, sir.
find out the restriction on the maximum load. I mean the value of maximum load. To do that,
Yes,
we are
sir.
taking this rectangular characteristic of the Zener, right?
Okay.
So at the maximum load, what is happening? The Zener is operating here. It is not carrying in current through it, right? So the
Yes, sir.
Zener is not there. You can see the Zener is not there. So if the Zener is not there, and
Okay.
again we have to consider the worst possible condition. So minimum value of input voltage you are considering,
Yes,
right?
sir.
So if the
Yes.
Zener is not there, whatever value across RL or whatever the voltage across RL, that comes from the voltage division law. This. So from here you can find out RL. So if you this is the minimum value of RL that you can have even at the lowest voltage. Now if you are increasing the value of RL means if you're reducing the load, what is happening is the Zener comes into action once again because the voltage across it is increasing and it comes into action and keeps the voltage fixed. So the output voltage never changes, even at the least voltage, least input voltage. So if the output voltage does not change even at the least input voltage, it will never change at the higher values of voltages also.
Okay. So this RL you have calculated a function of RS and V in min. This now suppose if we are calculating this RL, suppose we are connecting this RL at the output, which is a function of RS and V in min. Sir, at that time,
No, we are not connecting this RL as a function of this. This is the minimum value of RL that we can have. We can calculate any
yes, sir.
constant value of RL which is more than this or equal to this.
Yes, sir. Yes, sir. We have some value, some ohms of value we have for this RL. Now we are connecting this there across the Zener. Sir, now it will draw the same amount of current, which without Zener we have calculated this RL min. Now if you connect this, it will draw same amount of current because voltage is same.
And Zener is not working at that time.
Zener will not be working
If the voltage input voltage is at its minimum value.
Yes, sir, at its minimum value. So Zener won't regulate. Zener won't regulate the output voltage. Won't be constant. Won't be 12 volts because Zener is not getting. Yes, sir. Because Zener is not getting sufficient current.
We have calculated RL such that at the minimum value of the input voltage, also the output voltage equals Vz. Then why will it not? From this equation, you calculate RL, na? Okay, let me write RL equation. Maybe that is creating the confusion. Just a minute, give me some time.
Okay.
So VZB, I'm writing from here.
Okay, sir.
Equals V in minimum by RS by RL plus 1. So what we have is RS by RL equals V in minimum by VZB minus 1. So RL is this thing inverse V in minimum by VZB minus 1 inverse times RS.
Yes, sir.
Right? Now what is the confusion? You are saying Zener is not regulating. Let us not regulate the Zener. Let it not regulate. At the end, we do not care whether the Zener is regulating or not. At the end, we want whether the load voltage is fixed at VZB. We bought maybe a 3.34 volt Zener. We want the output voltage to be fixed at this value. At this condition, at this extreme condition, what is happening is the Zener is not working. But we have calculated the minimum value of RL such that, or maybe we have connected the RL value, calculated value such that even in this condition 3.3 volt is coming. How is it coming? Because voltage divider action. Then how will the voltage fluctuate? The voltage cannot fluctuate now. You tell me a situation where the voltage can fluctuate.
Sir, voltage can fluctuate only when the current through the Zener is not sufficient for the Zener to maintain constant voltage across it. That is the only point at which it will suffer.
See,
current
right
through the
now we
Zener.
have some voltage. Okay, Zener is not operational. Some V in which is at its minimum value. Okay.
Okay, sir.
RS RL. Now, how will the voltage fluctuate? How can the voltage fluctuate? This is not operational at all.
Okay, sir. Now voltage will not. It will be a constant. Voltage across RL is constant now.
It will always be constant. Okay, you tell me a situation where it can fluctuate.
My doubt is only when this Zener comes into picture.
When we
Uh,
come into picture, suppose V in increases, V in is fluctuating, suppose it has some nominal value above which it is fluctuating. Now it is at its minimum value. Now if V in increases, what will happen? By voltage divider rule, the voltage across RL, VL, that will increase. If that increases, immediately this Zener comes into play and maintains the output voltage at the breakdown voltage. It cannot fluctuate.
yes, sir. But sir, actually, when calculating this RL, they are assuming this is yes, and I understood what you have said, sir. But when we connect back the same RL here, the Zener will not get sufficient current to keep the voltage across it constant. The Zener will get the current less than I mean, which means it will not have voltage across it constant. If you connect this, if you connect same RL what you have calculated here back, if you
See,
connect at the output.
these calculations we did keeping this characteristic in mind.
Okay, ideal.
Hmm.
Okay, sir. Okay. Yeah, that's my doubt.
For
Okay, they have taken
practical,
that characters. Yeah, okay.
they have taken
Because
this one.
okay, practical. Okay, they have taken ideal for this calculation.
No, if they have taken which one? One or two?
I think they have taken one.
If they have taken one, then that comment cannot come. That if the current is below I and I mean, then it cannot uh, maintain the voltage.
Okay.
Because I mean is 0 here.
Yes, sir. Okay. So I think I'm confusing with the ideal case and practical case. Okay, sir. So yeah, if this characteristics is there, then it is good, sir. It is correct, sir.
If you want to use the real characteristic which actually looks like this, it not only comes out like
Yeah.
this but also goes out like this. Goes out
Yes,
like
sir.
this. Then you have to first fix a range where you want to operate. How will the range be decided? Depending on how much tolerance you have at the load voltage. This much tolerance you can permit at the load voltage. Depending on, you can calculate the range of current that you can have at the load. Sorry, not the load, in the diode, in the diode,
Zener.
yes.
Zener, yes.
Depending on that, since you already know the load, you have to calculate this RS.
Okay. Okay, sir. I think that's. Sir, I have another doubt.
Yeah.
Sir, loading full loading means we always talk with respect to current only, no, sir.
Yes, always.
If current through the load is maximum, we say it as load is high.
Load means current.
Yeah, load
So
means
when
current.
you say higher load means lower resistance.
Yes, sir. Okay.
Or
Sir,
lower impedance.
sir, in that there is a constant current regulator circuit, sir, with Zener. They have maintained a constant current regulator cycle through the load. For some ranges, constant current will flow. Sir, in that range, how to calculate, in that case, how to calculate the maximum load at the output? I don't know. If the current is constant.
I think that was discussed in the lecture. I watched it last week. I don't remember it now. Wait. Where is the current source? There is an application, or do you remember in which lecture it was?
I think it is application of shunt regulator.
The shunt regulator. Yes.
Yes, sir.
So generally, see, the thing is, any current source, just like a voltage source, right? What you have what we say is that this is an ideal voltage source, right?
Yes, sir.
So an
Yes, sir.
ideal voltage source can source you infinite current, okay?
Mm.
And irrespective of the load, the voltage across the load is constant. But in reality, what we have is a series resistance in
Yes, sir.
with the supply voltage. So because of the series resistance, now this whole thing
Mm.
is the voltage source, okay? Because
Yes,
of the
sir.
series resistance, it cannot supply you infinite current, because there is a loss in the source, power loss in the source,
Yeah.
which is given by I squared Rs. So you cannot short circuit, and because of this resistance only, with changing load, your load voltage also changes. So it is no longer a constant voltage source. Lower the resistance, lower is the regulation. Similarly,
Okay.
this is an ideal current source, okay? What is an ideal current source? An ideal current source, see what is happening for a voltage source. Voltage source, increasing load means increasing current. Current source, increasing load means increasing voltage, because the current is constant, okay? So this is an ideal
Mm.
current source I.
Mm.
Just like we can short circuit an ideal voltage source, we can open circuit an ideal current source without any damage to it, okay? And
Yes.
any number of loads you connect, remember, in voltage source we connect loads in parallel. Sorry, just a minute.
Yes, sir.
In voltage source we connect loads in series, sorry, in parallel. But in current source we have them in series.
Mm-hmm.
So we have to have loads like this. So load 1, load 2, load 3, and the switches will be in parallel to them, right? If I
Mm.
am
Yes, sir.
turning on a load means I am opening that switch, right? Opening means turning on the load,
Mm. Yes,
right?
sir.
Ideally
Yes.
speaking, ideally speaking, so what is the maximum load if I keep turning on? So if I keep increasing the series impedance, so the maximum impedance means open circuit, completely open circuit,
Uh,
is the maximum load that the current source can have. Why? Because it is a constant current source. The current must keep flowing. So it is flowing through this dielectric path, which has infinite
mm.
resistance. So the voltage across it is infinite, just like the
Mm.
infinite current in short circuit of an ideal voltage source. Now, a real
Mm.
current source has a very large value of resistance connected to it in
Mm.
parallel. Ideal voltage source has small resistance in series. Real voltage source has small resistance in series. Real current source has a large resistance in shunt, okay?
Yes.
Now you cannot open circuit it anymore, because if you open circuit it, the whole current is flowing through this Rs, and it is causing a power loss of I squared Rs. In the previous case, the power loss was large. Why? Because I was large. In this case, the power loss is large because the Rs is large.
Mm.
Okay.
Okay, sir.
So for any current source, so we can say in general that you cannot short circuit a voltage source. You cannot open circuit a current source.
Mm.
Okay.
Okay, sir.
So we live in a world of voltage sources. So all our MCBs are made such that if there is a short circuit, it will trip. Had this been a world of current sources, our MCBs would have been like that. If there is an open circuit, it will trip. Trip means it will short circuit the source. Now it open circuits the source, those MCBs would have short circuited the source. If you short circuit the source, what is happening? Whole current is flowing through the short circuit path, so power
Mm.
loss is zero.
Mm.
Okay.
Okay. For current
Now,
source, MCB should be shorting.
yes, but we do not get to see current sources in, never in powers, not, I should not say never, but not that frequently we see them. There are applications of current source. Now the circuit that I can see in front of me. So your question is how to find out.
Sir, Mike,
uh,
yes, sir.
anyway, I thought I will discuss, no problem in asking, but
Yes, sir, it will, some RS will be there on the left side. Okay.
okay.
Yes, sir. On the collector, some resistance will be there. That is a load resistance.
Hmm.
Okay, we can connect.
So my load is coming here,
Yes, sir.
right? And this is some RE, this is some VCC, this is the ground, right? So basically what we have here on our left hand side is the, we can say this is the shunt regulator, right?
Yes, sir. It's centered.
So this voltage Vz is fixed, right? Now we have base, emitter, collector.
Sir, Mike.
Just a minute. So yeah, what is the question?
Sir, what is the maximum? If I say maximum loading, if if I say if the load is a rated load is connected here, what does it mean, sir? That's it, because current is constant.
Okay, let me see if I can answer this. What was that? This is collector to emitter voltage, and this is a collector current, right?
Yes, sir.
So it is something like this, and it is operating in active region because I can see the beta values and all being used.
Yes, sir.
So if it is acting in this, say you are operating it somewhere here for some value of resistance, so some collector current is flowing, which is nothing but your load current,
Mm.
and as a result you
Yes,
are
sir.
getting some VCE.
Yes, sir.
Now this is the base current that is flowing
Yeah,
in opposite way,
flowing out. Yes, sir.
the base current that is flowing. So what we have is voltage across RE is equal to Zener voltage minus
VB.
the
Yes, sir.
base emitter. So if we increase, now you are saying that rated load means what is the maximum value of RL we can calculate, right?
Yes, sir. Maximum
Not
value of RL that
not
you
the
can.
minimum RL. We got it from this
Yes.
discussion.
Yes, sir.
Not the minimum RL. So suppose I am increasing the RL, I increased it to some extent. What is happening? Uh, means this voltage increases. If this voltage increases, then
Voltage in VCE will decrease. Or
wait, the current IE is Vz minus VBE. What is the emitter current IE?
VZ minus VB by RE.
Wait, IE is Vz minus VBE by RE. Is the current. Now if you are increasing this, That means now you need lesser current. No, wait. So this IE that was coming from here, that must be getting diverted somewhere.
Yes, sir. IB and IC.
So one current was coming right here, other current was going this way.
Yes, sir. So into that resistance on the left side.
Hmm.
Okay.
So that is going down. So
Hmm.
whatever current is coming here, this plus this current is going down.
Yes, sir.
And that is increasing the voltage. If this voltage increases, this voltage will increase. So what do we mean by IB increasing?
Sir, I think all the currents are constant only. IE, IB, everything will be
See,
constant.
ideally everything is constant, but since you are talking about uh,
Mm.
maximum, see what is happening in a current source, there is always some current flowing through the shunt resistance. Now since it is very very large, the current through is very small. Now
Mm.
increasing load means increasing RL, means more current will now flow through the shunt resistance, right?
Mm.
So if this IE was constant, see if I write here VCC equals IERE
Plus VCE.
minus VCE
Okay, okay.
plus the load voltage VL. Now increasing RL means increasing of this. Increasing this, if I, this is constant, this is constant. Now increasing this will increase this, right?
Mm. Yes, sir.
Increase this will increase this. So I think the limit is coming from here. You understood? What I did is I applied KVL in this loop,
Mm. Yes, sir.
and that gave me this equation. VCC is
Okay.
constant, I is practically constant.
Okay.
So increasing load resistance has to increase this VCE. So VCE means on the same
Mm.
characteristic we're moving this side. There is a limit beyond which
Mm.
this breakdown happens. So I think this will dictate the maximum load voltage, maximum load resistance.
Mm. Okay. Then VCE decides what load we can connect here.
Yes, looks like that.
Okay.
This equation is correct, right? Did I do any mistake in writing the signs?
Uh,
VCE when I write it should be plus minus. So it should be minus VCE. So it is correct. So VCC is IERE drop minus VC increment. Again VL is like this. Yes, it is correct.
okay, sir. Okay, okay, sir. We can proceed
This
further.
is understandable also from here. You see, For a transistor, more we go this side for the same value of IC, that means
Mm.
more loss is happening in the transistor. The same thing that happens in a regular current source also. More
Mm.
load means more loss in it.
Mm. Okay. Okay, sir.
All right. So this week is for switched DC-DC converters, uh, which are non-linear and at the same time efficient. So you might recall that at the very beginning of this course, during the very initial classes, I used to say that there are three components in electrical engineering, namely the inductor, capacitor, and switch, which we can practically consider, not practically, which we can ideally consider lossless. Others we cannot ideally consider lossless. So these three we can consider lossless, and if we have any circuit which is a network of these three things, then that circuit is ideally 100% efficient circuit. Okay. Now in all the polytronic converters you will see resistance connected, but that is only as a load, because power converters or any circuit with any semiconductor circuit without the load does not make sense, because if there is no current, the devices themselves do not turn on. Could you please mute yourself? So
Yes. Sorry, sir.
it does not turn on. So all the resistances that you will see in the switched converters are loads, not part of the converter. So I will now like to take doubts from switched converters.
Sir,
Yeah.
could you explain the diode voltage in buck converter, sir? What is making the diode voltage to diode to get forward biased when the switch is off?
Okay.
What is the voltage appearing across a diode which is making it to on?
Okay. So let me draw the buck converter. This is, sorry, a buck converter. Okay. So we have V in here, we have V out here, and the load. So L, C, D, S. We'll look at the operation first. So I will first draw the switching waveform. Okay. So in this high condition, switch is on. In this condition, switch is off. All right. So what is happening to the, say, inductor voltage when the switch is on? When the switch is on, the inductor is getting a voltage which is equal to V in minus V out, right? Now what is happening to the inductor current? Since the inductor voltage is positive and we know that V is L di dt, so a positive inductor voltage, how do I know that it is positive? I will come to it later. As of now, take my words. So the current in the inductor will be increasing. Okay. So the current through the inductor, and this is VL. Okay. If I only draw the waveforms without marking the current and voltage polarities, that doesn't make any sense. Okay. Whenever you do, make sure that you are marking them on the circuit. So this we have right now. Our switch is closed and this diode. So what is the voltage across the diode? We'll see. The voltage across the diode is this is closed, so the node voltage here is V in and this is 0, so voltage across diode is minus V in, right? Yeah. Now what happens when we close the switch? See, as soon as we close the switch, what is happening is a current was flowing when the switch was closed. A current was flowing like this. The whole inductor current was flowing like this, and I close the switch. When I close the switch, what happens is the current here instantly gets interrupted. The current here instantly gets interrupted, and the circuit now looks like this. The circuit now looks like this. This is the inductor, capacitor, this. The diode is here, but not yet conducting. Okay. So I will write VL, VO, V diode. Okay. Now if I apply KVL, what is happening is VL drop, VO drop, VD drop is 0, right? This is the KVL that what happened. So this is the KVL equation that we have here. That is not true only when we are turning the circuit on or off. This is a general equation that we have. Now what happened is a current was flowing, IL current was flowing. It was at this point when we interrupted the current. Now we know that VL is L di dt. We interrupted the current. You see, as soon as I turn off the switch, this current has no path to pass. It cannot pass through this supply because this source is off. It cannot pass through this diode because diode is off. So it has no current and no path to flow. So what is happening is, since the current has no path to flow, means we are suddenly interrupting the current. That means we are getting a large negative value of didt. We discussed this some time back, if you remember, that if I have an inductor and a switch, and if I suddenly turn off the switch, if I suddenly open the switch, the whole voltage comes across this because of this LDIDT, this kind of waveforms we discussed. So this large voltage is coming and that is negative. So this equation, this must hold good always. So VL suddenly becomes suddenly tries to become very small. VO cannot reduce that first because it has a capacitor. Capacitor voltage cannot reduce that first. So only thing that can happen is VD will now try to increase. Now when the switch was closed, VD was 0. Sorry, when VD was minus V in. Now since VL has reduced very fast, Vn will try to increase, and as soon as it reaches 0 from minus V in, this diode turns on. Because what we mean by forward bias of a diode means Vd is positive, or maybe if you want to consider non-ideal diode, Vd is say 0.7 volt. So maybe your input voltage was 50 volt. So before you opened the switch, the voltage that was coming here was 50 volt. Look at the polarity. In this polarity it was coming 50 volt. Sorry, in this polarity it was coming minus 50 volt, we have given the polarity like this. So minus V in 50 volt was coming. Now as soon as you open the switch, this inductor current which was being interrupted by the switch now forces this voltage to increase. Now it increases from minus 50 volt, and as soon as it reaches 0, the diode becomes forward biased, or maybe as soon as it reaches 0.7 volt, the diode becomes forward biased. And as soon as the diode becomes forward biased, now the current gets a path to flow. It flows like this. This is why the diode turns on as soon as you open the switch. The inductor current forces the diode to turn on. Is it clear?
Sir, the inductor voltage negative, no? The switch end
Inductor
voltage near the switch end should be negative, no?
inductor voltage near the switch, what you were saying?
The inductor voltage near the switch end should be negative in order to turn on the diode.
No, you see, what we do is we draw this circuit and we mark all the voltage polarities. We mark all the voltage polarities like this, and we always talk in terms of these voltage polarities. So if it is positive here, that does not mean that this is at higher potential than this. No, I am assuming this as the means, or in other words, you can say whenever I am saying inductor voltage, I am talking about voltage of point A with respect to point B. That is the meaning of this plus and minus.
Yes, once the switch is off, how the diode is forward biased?
That's why what I discussed, that when you are turning off the switch, that means you are interrupting this inductor current. So if you're interrupting this inductor current, that means you have a large value of LDIdt, large negative value of LDIdt. This equation must hold good always. So if you have a large value of LDIdt, that means a large negative value, that means if you have a large negative value of VL, VO cannot change that first. So to make this equation valid, VD must increase. VD was initially minus 50 volt. That increases to 0. As soon as it is 0, diode is on. And the current now gets a path to flow.
That's what. Who is making the diode to make it 0 volts from minus 50?
Did you not follow this explanation?
No, sir.
See, when I am saying L didt, this means when the current is increasing, didt is negative. Understood?
So diabetes is also positive, no? When current is increasing.
Current is
Oh, I'm
increasing.
sorry.
Diabetes is positive.
Yes. Sorry. It's increasing means didt is positive.
Okay.
Okay. Now I turned off the switch. I opened the switch. Some current was flowing. Suddenly the current has no path to flow. You were there in the class when I discussed this thing, inductor circuit and turning off the circuit suddenly.
No, sir. No, sir.
Okay. So suddenly the current has no path to flow. So it will try to reduce. Right? KCL. The current will try to reduce. And that reduction is very abrupt. Very fast it is trying to reduce. So when the current is trying to reduce, that means your didt is now negative.
Yes.
Right? So if didt is negative, L didt is negative. AI DIT is negative means voltage across the inductor is negative.
Yes.
Now look at the equation and look at the circuit. This is VL, this is VO, this is VD. Okay, if I write KVL, it will be VL plus VO plus VD equals 0. Correct?
Yes, sir.
You're telling that voltage across the inductor remains same
No, I'm
even
not
after
saying
switch
that.
is on.
No, I'm not saying that.
You have written it.
Voltage across inductor remains same.
Yes,
No, when did I say that?
as in the case of switch was closed.
No, you see, the voltage across inductor is falling. See here.
Okay.
So this voltage suddenly has a tendency to fall very fast. Why? Because the current through the inductor was interrupted.
Okay.
Now in this equation always holds. Be the switch is off, be the switch is on, this equation always holds. Now the if this term is trying to reduce suddenly, that must be compensated by these two. VO cannot change that first because there is a capacitor. So VD will increase first. Before turning on, VD was minus 50 volt. The diode was blocking 50 volt. I am assuming input voltage to be 50 volt. So the diode was blocking the input voltage. Now it is increasing. It is increasing from minus 50 to minus 40. This way it is increasing. It is increasing to 0 or maybe 0.7. Why is it increasing? Because VL is reducing fast. Someone has to compensate. VO cannot. So diode voltage is increasing. As soon as it reaches 0.7, it is turned on. Diode is forward biased. So now this diode is practically short circuited. Or if it is 0.7, we cannot say short circuited. And the current now has a path to flow. Current will flow like this through the diode.
Okay, sir.
I cannot draw the diode anymore. So basically the inductor current is forcing the diode to turn on. It is suddenly applying a high voltage across the diode to force it turn on. But the diode does not need that high voltage to turn on. As soon as the voltage is 0.7, it turns on.
But here the current which is showing is the inductor current,
Hmm.
and the downward is inductor voltage.
Hmm.
In inductor, the current lags the voltage. Where is that in the graph?
Okay, it looks like you missed those initial classes. Inductor, current, lags, voltage, all these things
No,
are,
in this waveform.
see, those things are all valid for steady state AC circuits.
Hmm.
I think we had a long discussion on this.
Because your audio is also muted, no? The two classes, we cannot listen to that.
No, this video was proper. These things happen. It all depends on who is
Two videos
traveling.
were muted.
No, there was a
Okay,
last
two
videos,
videos were
but
muted.
these were quite old. Anyway,
So what happens
this is
during the
this is a DC
transient?
circuit. This is a DC circuit.
Hmm.
The inductor current is like this. And the inductor voltage is like this. It is simply that if the inductor current is increasing, voltage is positive. If the inductor current is falling, voltage is negative.
Sir,
Yes.
There is no resistance in this circuit, then which component decides the slope of the current current rise in the inductor?
Uh, the slope of the current rising
Rise.
in the inductor, that is never decided by a resistance. If you consider a DC circuit with only an inductor,
Yeah.
then V equals L di dt. The slope of the current is decided by the voltage and the inductor
But
value.
in this circuit, if it is ideal inductor,
Hmm.
there what will be the slope of the current rise in this ideal circuit, ideal inductor case?
So I will draw two circuits. One is the condition when the switch is closed, other is the condition when the switch is open. Okay.
Yes, sir.
So this is the condition when the switch is closed.
Yeah. So there is no capacitor, sir. It is only ideal inductor.
This is the buck converter circuit.
Okay. Okay.
I am drawing the buck converter circuit in two cases, when the switch is closed and when
Okay,
the
sir.
switch is open.
Mhm.
So this is the case when the switch is closed.
Yes.
This is the case when the switch is open.
Okay.
Now this is V in, this is VO. So what is the voltage across inductor?
V in minus V0 by
V in
L
minus V naught
V naught.
is
Yes.
VL. So the di dt slope of current is given by this
V in
VL by L. That means
yes
V in minus V naught by L.
by L.
Okay. Inductor
To
will
be
decide.
precise, delta I will be V in minus V0 L into dt.
Yes.
Mm.
Since
Okay.
the current rise is linear,
Yeah.
we can consider them as delta I and delta T. So
Mhm.
if you want to have a peak-to-peak ripple in the inductor current, that is delta I, which is given by delta T times V in
E
minus V
divided
naught by L, which is also equal to, what is delta T? Delta T is DTS.
DTS.
Yeah.
DTS is the turn on time. D2 ratio
Mm.
times the time period of the frequency switching times V in minus V naught by L. So they
Yes.
all together decide the ripple, and the slope is decided by the voltage across inductor
Mm.
and
And
the
the inductor
inductor value.
inductance value.
Whatever
Okay.
DC-DC circuit you are going to study, not only in this course, in later courses also, it's all about how you are treating the inductor.
Yeah.
Even if it's a completely new circuit, just look at the inductor, draw the voltage waveforms across it, then draw the current across it. You will get to know how it works. It's all about the inductor in DC-DC converters.
Yes, sir.
So during turn off time, shall the same thing we can
So
use the
during
same
turn off time,
equation?
what is happening is
That V
this
in
is
will be
VL.
0.
So my VL is minus VO,
VO.
Mm.
right? So what is happening for dTs period of time? My inductor voltage is V in minus V0.
Minus V naught.
1 minus DTS
For the rest of the time, it is minus V0.
Minus V
minus
naught.
V0.
And we studied that average voltage across an inductor
Zero.
at steady state
That is zero.
over a complete time period is 0.
0. Yes.
So if we can divide it, sorry, during this time it is V in minus V naught, and it's constant, not a function of time. So we can directly write it as V in minus V naught times dTs. I'm jumping a step. If you cannot understand, tell me. minus V naught
Sir, one more term has.
missing something. V
Okay,
in dt
correct.
is
Correct only, sir.
so V in dts minus V naught dts minus V naught ts. Ts I will remove all the ts. So V in d minus V naught d minus V naught plus V naught d is 0. They cancelled out. So what we got is V naught is d Vn.
Sir, can you explain that the inductor part?
Which part?
That inductor in steady state you are explaining?
We explained this in one class that the average voltage across inductor at steady state is 0.
No, not okay. Okay.
But this is for the continuous conduction mode. If it is not continuous conduction mode,
The average
will
voltage across inductor at steady state is 0. That it doesn't matter in which
either
mode it is
it's whether
operating in.
okay. But this expression V0 is equal to D into Vn will be changed if it is DCM.
No. Yes, it will change. It will change.
It will change.
Hmm.
It will no more the factor of D only. It will be factor of load current.
It will be factor of frequency also, load current also, inductor also.
Inductor also.
No, not
Inductor
inductor,
load
not inductor. The condition depends on inductor, but it depends on the load current and the frequency, I think.
frequency. Okay.
Inductor, does it come 12 by? No, inductor also comes, yes. I forgotten the equation
It is
exact.
FL 1 upon something FL
Hmm.
into I0.
Yes,
I think
frequency
so.
and everything comes into play.
Yes, yes. It is not the as linear as D.
Yes, it no more remains linear. It becomes dependent on load also.
So what happens in the dynamic condition then?
No, he's talking about discontinuous conduction. See,
No, I'm asking regarding dynamic condition of the inductor.
dynamic condition means
Sometimes it is DCM, sometimes it is CCM.
no, it cannot be sometimes DCM, sometimes CCM. Depends on the load.
Load depends on the load, but the controller will take corrective action for the both the states.
If you have a controller, then yes.
So, sir, I asked that inductor current lags the voltage, but where it is in the waveform?
So this is the inductor current and voltage. Okay. So you can say in this fashion that let us consider 50% duty ratio. Okay. Now if you have 50% duty ratio, then what we have to do is, since these are not pure sinusoids, you have to consider the fundamental. Now if I draw the fundamental of the supply voltage, not supply voltage, sorry, inductor voltage, it is like this.
Yes.
And for this it should be like this. The peak is here, so like this.
Sir,
Hmm.
sir, what we are doing now, sir? Are we finding the harmonic components, or what we are doing
No,
now?
he's asking that we know that inductor current lags voltage by 90 degree.
Okay.
So whether that we can see, that is here. But yes,
Okay.
harmonic analysis in this voltage and current doesn't make any sense because these
Only
are
the
DC
fundamental
circuits.
will make.
No, no, no. When you are saying fundamental, that is also a kind of harmonic analysis. That doesn't make any sense here. These are DC circuits.
AC circuit, no.
But when we are seeing this phase difference of current,
Again, that has no significance here. I am showing this
okay,
because
okay,
he
okay.
asked.
No, no, sir, I didn't understand. I didn't hear his question. That's why I asked, sir.
Yeah, yeah. He asked how do we see that phase lag. So if you want to see the
Okay.
phase lag, you have to draw the fundamental and see. But
Okay.
again, that is of no significance here.
Because this is DC circuit.
Yes.
Okay.
Sir, it is DC or AC? It is switching, no?
No, no. The current is DC. No.
Current is DC having a ripple with some.
Voltage, inductor voltage has to be AC, be it any circuit.
Hmm.
Otherwise, the inductor current will keep on rising. So whatever circuit in the world might be, inductor voltage is always AC. If
So
not
current
one,
is
yeah.
current is DC plus AC. It is not only DC in the inductor.
Yes, it is a DC plus AC.
DC and AC, right?
DC
So
and
you can
AC.
see.
No, no. See,
Yes.
what is the definition of DC? Is this not a DC?
Yes,
This
it
is
is AC.
It is not changing polarity.
Hmm.
It has high frequency components, but it is DC.
Okay, then current through the inductor is DC.
If you make the inductor value very, very high, then the current will become practically constant.
Hmm.
The voltage waveform of the inductor will not change, but the current will become practically constant if you have unnecessarily high value of inductance. So now, since we have come this far, look at this equation. Delta I is this. Okay. Now, if you are continuously operating in CCM, then V naught you can consider a constant. Okay.
yes,
Now,
sir.
if V naught is constant, then the output current is also
Constant.
Now I can write from here. Why did I write LS here? L is equal to dTs. I am writing as D by Fs. Okay, times V in minus V naught by delta I. You have now, for certain condition of all these things, you have certain ripple in the inductor current like this. Okay. Now if you increase the supply frequency, not supply frequency, sorry, if you increase the switching frequency, what will happen? The D2 ratio is same, so the time for which the current was rising now reduces. The time for which the current was falling also reduces, right?
Yes.
So in other words, with increasing frequency you have smaller ripple for the same value of
Inductor.
for the same value of inductor. But say you do not need this much small value. Suppose you are happy with 20% ripple in the inductor. So what you current ripple in the inductor, so what you can do is with higher frequency you can reduce the value of inductor. If you have if you remember what I was discussing at the very first class, I said that increasing frequency has definite advantages. One of them is that the circuit becomes very small. It is because this, keeping everything else constant, if I increase the frequency I can reduce the inductance without affecting much, without affecting anything, ideally speaking, on the performance. So if I have smaller inductor, means my whole circuit footprint becomes smaller. Not only that, increasing frequency, as you can see, reduces the current ripple. So this inductor and capacitor is nothing but a filter, low pass filter. So increasing frequency will reduce my requirement of capacitor value also. Say I am happy with a 2% voltage ripple at the load. So increasing frequency, I can reduce the capacitor value also. So basically increasing frequency with reduce this filter size, I will have a smaller circuit.
But sir,
Yeah.
by increasing the frequency, there will be more losses. To
Which
overcome
losses?
that, you had switching losses.
Switching loss. I was about to tell that. We established in some lecture while solving some problem that switching losses is directly proportional to frequency. So
Yeah.
increasing frequency will direct, because increasing frequency means the switching phenomena is happening again and again,
Yes.
faster, and the same losses are happening faster. So we have more loss.
Yeah.
So increasing frequency comes with this drawback that
Yeah. So
switching
what is the
frequency
trade-off?
increases.
By increasing the frequency, you are saving the space in terms of lower value of L and C. But due to increase in the switching losses, you have to put bigger heat sink. So if I see
So
the
there
size
are
point of
two
view,
things. One is bigger heat sink.
yeah,
A bigger heat sink is not a very good solution. What I am saying why is that, yes, you are saving the switch by using a bigger heat sink, but at the end your efficiency is dropping.
yes, yes,
Okay, so the trade-off that you are asking is um, the switches that come, they have certain capability of handling power loss. Okay,
yeah,
you may want to operate somewhere not very close, but maybe say somewhere that keeps the temperature more or less in your control, and the volume of the circuit is also not shooting up from the application requirement. But you have, if
mm,
you have to have a very high frequency circuit, then the solution is resonant converter.
okay,
Resonant converter is not covered in this course. It cannot be also. It's a fundamental course on power electronics. I will just tell you what it is. So suppose a switch was off and it is getting turned on. So if the switch is off, that means the voltage was full
mm,
and the current was this. Now what happens is current rises,
yeah,
maybe voltage falls from somewhere here. This is where we have the power loss.
yes,
Resonant converter, what is done is, apart from the output LC filter, there are other LC circuits introduced in LC tanks introduced in the circuit, which cause, and those are high frequency, okay, and which cause this voltage, instead of going like this, to resonate, shoot up like this maybe, then fall. And once it falls to 0, then only the current increases. So in this way we can ideally have zero power loss in the switches,
Zero switching loss. Yes.
zero switching loss. So this
Yes.
specific phenomena that I showed you here is called ZVS, which is known as zero voltage switching, which is happening during turn on. During turn off, what can happen similarly is ZCS, which is zero current switching. But yes, again, everything comes with some cost. With this, what we are getting is we are reducing conduction losses. Sorry, we are reducing switching losses, but conduction losses are increasing. Because in zero voltage switching, zero current switching, what will happen is the current that was previously dropping like this, now we are forcing it to resonate and drop like this. So we are having larger conduction loss.
Yes.
And it is load dependent also. You cannot ensure ZCS or ZVS for any value of load. That is ensured only for a given range of load.
We cannot have PWM.
PWM?
We cannot have PWM type of control, like D control. Here it will not, we have to control the frequency.
Okay, that may be the case in some converters, but as far as I know, frequencies, I don't know.
Purely resonant. It is for purely resonant converters. If it is quasi-resonant or switch resonant, then
Maybe
it is
there
compromised
are
between.
circuits, I'm not very sure. I'm not sure about that.
Sir,
Yeah.
sir, for making this ZVS and ZCS,
Hmm.
for each switch, do we need to add any additional?
I have forgotten the circuits, but yes, you have to introduce additional capacitors and inductors also, I think. If you want to have a good discussion, I want to see a good discussion on resonant buck converters, you can look at this book by P.T. Crine, some elements of power electronics or something, the name of the book. They are here. Two examples are very well solved for ZCS and ZVS buck converters. You can see how it works. Crine, P.T. Crine, Krein.
Oxford University.
Yes. Philip T. Crine. Okay, should we start the problems then, or you have some more doubts?
Sir, I have a doubt in present live assignment 6, question number 6. They have given the slope of the buck boost converter. From the converter given values, it seems the duty ratio seems to come in the value of 1.7. For buck boost converter, sir explained that it has 3 ranges of D. For buck operation 0 to 5. And
No, if you are getting duty ratio more than 1, you must be doing something wrong. But the question I
Simply
can
they have given the two slopes. But calculate if we calculate the V output divided by V input ratio, it is coming simply 2.4 only, which gives D as 1.7143 only. Maybe I don't know where I am going wrong.
okay, but I
Simply they
cannot
have given the slope of the IL waveform.
discuss current assignments in live classes because there that would depend. I mean, that directly affects your certification and all.
Or you give me some hint to solve that problem?
Which
Instead
problem?
of rather than solving, can you current
Which what is the
assignment
number?
question number 6?
If you have slope of the current.
Yes, sir. Slope of the current is given. For buck boost, it is VI by L. VI by L and V naught by L. I mean both on and off situation, on and off switching instant they have given. So if I take the ratio of V naught by Vi, it is coming to be 2.4 only from the given question. If you could see the data, it would be helpful. During on time, the slope is 2381, sir. During off time, it is 5714. So the ratio is V output by V input is 2.4. So as per the solved lecture, if V output
Okay,
is
wait.
2.4 times Vi, which defaultly
Okay,
gives D as
okay.
1.71.
Wait. Okay.
Why I am raising this? All the questions are interlinked questions. If anything goes wrong, all the questions are becoming wrong. That's why, sir.
Inductor value they have not mentioned.
Sir, inductor value is not given. It is a asked parameter.
Okay, wait.
Slope of both on and off time is given.
Okay. I'm seeing. Just a minute. Let me think. Okay, so if you have both, then during on time it is this, and during off time it is V out.
Output by L.
So if we have the slope during V out, slope during the so what we have is V output by V input is D by 1 minus D. Buck boost, yes, D by 1 minus D. So derivative of that, we have this. So no, you are doing something wrong. Question is correct.
Sir, actually it is V output is minus Vi into D divided by. That means V output is Vi into D divided by D minus 1, right? You are putting 1 minus D. As per sir's lecture video, V output is V input into d divided by d minus 1. Can you give me the ratio?
This is the equation. If you take magnitude of V out, if you take magnitude of V in, then this is the ratio.
Okay, okay.
If in the boost converter, if you take the output voltage polarity like this, then maybe what you are saying is correct.
Okay, 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 sir. Let me solve
This
it this
exact
manner.
concept I am discussing many a times from the very first class, that any circuit, before you solve the circuit, how you are putting the polarity of voltages
It
and currents
matters.
across the components, that matters. You have to stick to it.
Okay,
It does not
okay,
matter whether that is correct or not. If it is not correct, it will come negative. It can even keep varying also.
okay. Okay, sir. Okay, thank you, thank you.
Sir,
Yeah.
can I discuss the buck boost converter here?
Buck boost converter, I am afraid I'll be able to complete.
There only one hitch was there, that phi, sir has told in his lecture that he has written the equation of phi, the flux. Okay, so we understood the buck boost converter in a context with the L, in delta I, but he has modified that delta I expression into in terms of flux.
See, the thing is, phi or n phi is Li.
Li.
As long as you are operating in the linear region of the BH curve, your current and flux waveforms look the same.
Okay.
So
But how the scaling factor of phi I in terms of I?
you can say this phi equals Li by n.
V in divided by that L.
No.
Initially,
You want to know the relation between phi and I, scaling factor, right?
yes, yes, yes.
It is this one, this equation.
Okay. Okay, this is the equation. Then he has scaled down that delta is equal to VL, V in divided by L into delta
Basically, V is d psi dt.
the
So you can say that delta psi is
hmm,
V delta t.
V delta T. Okay.
You can also say, if you're talking about phi, then this equals V by L. Sorry, delta t.
V by N into delta T. Sir has not written that delta T. Delta T will be there all the time. Okay. That will be
Okay.
phi.
Hmm.
But when we are talking that delta phi in terms of magnetic flux density, that delta phi will be n phi, and a number of turns into
You
phi
are talking about flux density.
plus flux density, because that delta phi has to correlate with that delta B, isn't it?
Yes, now we have phi. Now, if you have to talk about flux density, now one more thing you have to bring in the picture, which is how does the inductor looks.
Yeah.
If it is like this,
Hmm.
and say if the flux is flowing like this, if you have a similar body here like this, then, and if you have the winding here, then the
Okay.
cross section that the flux is getting to flow,
Okay.
because B is flux density.
Phi divided by A.
This A is area of cross section of the magnetic circuit where the flux is flowing.
Okay. And whatever we have drawn, that delta B, delta phi divided by area of cross section.
Yes, that will give the delta B.
That delta B, beta AC, that will be the flux density of the AC ripple. delta phi
Yes, the ripple, the
ripple,
peak ripple.
ripple. My
I
question
will
is
discourage you to mention the term AC.
AC. Okay, okay, okay. Peak to peak ripple, not okay, okay. That is because of that delta I.
Hmm.
That is coming because of delta I. Delta phi will come,
Hmm.
and that will be beta. Okay. But my question is that at the start of the cycle, it is starting from I to I max, okay, and this will give rise to delta phi. But how to get that I related B? That is B AC. Just for sake of understanding, BAC is riding over the BDC in flyback और डीसी और बक बूस्ट में तो ये बी जो डीसी है
Sorry,
उसका
could
वैल्यू
you please
कैसा
speak in English?
हाउ टू गेट दैट बीडीसी because it is raised over the BDC term.
Okay, how to get that?
How to get that BDC?
So we will not talk about B, okay?
Okay,
Because we will talk about I. Because everything, if you have I, you can linearly get to B.
okay.
From I, you get phi
The N
using
phi
this
is equal to
equation, and
Li.
from there you can get B. So we'll talk in terms of I, okay? Now, since
Okay.
we are talking about buck boost, we will see like this only. So this is the
Inductor.
buck boost,
Hmm.
and this is okay. So I will mark all the currents.
Okay.
Okay, capacitor I have drawn opposite. I'll mark the currents. So what is the current? Say this current is ID, this current is IL,
IL.
this current is IC,
I see.
this current is
IR.
IO. Okay. Now I am applying KCL at this node,
Okay.
right? If I apply KCL at this node, what do I have? I have IC plus IO is ID.
Okay.
True. Now we discussed this that at steady state the average current through an inductor over a complete period is 0.
0.
If I take an average of this, then what we have is ID is IO,
IO.
average value,
Average. Okay.
right? So for a buck boost converter, what we can say is average diode current is average load current.
Average.
Okay. Now, if we look at the inductor current IL, it is like this,
Okay.
and the
One portion is through IL.
diode current, if I draw, when the inductor current is rising, diode is not conducting. Diode current is like this.
Like this. We have to modify this IL also.
Why should I modify IL?
Because sometimes it will flow through IL and other time it will be ID.
No, inductor current can never be discontinuous.
Oh, okay, okay, fine.
I mean, we are talking about CCM, but
Okay.
inductor current is like this. So
Okay.
if it is
If
inductor
it
current,
is battery current, then it will be.
so this is the diode current. So whatever my average inductor current, that much is my input. I'm not sorry. So this is the diode current, and what else do we have is the source current, IS, if I write.
Yes.
So
Yes.
source current is this.
Yes. Yes. Complementary. Okay.
This is my source current.
Source current. Okay. Now my question is that these
Yes, I am
source.
coming.
Okay.
You wanted to know about how we get to know the average value of it, right?
Yeah, yes.
So if this, suppose the minimum value I am writing as I1 of it, the maximum value I am writing as I2.
Hmm.
If you do IL average,
Hmm.
just if you do say half into base
Hmm.
into height,
Hmm.
I2 minus I1, we got area of this upper triangle
Hmm.
plus base into I1, we got area of this rectangle. You understood, no? Two
Yes, yes.
parts I divided, this area and this area,
Hmm.
whole divided by TS.
Yes.
What you get is I1 plus I2 by 2.
I want to saturate.
So the average inductor current is I1 plus I2 by 2.
Okay.
And if you look at the diode current, this is 1 minus dTs. If you calculate, you will see the diode average current is 1 minus d times the average inductor current, and the source average current is d times the average inductor current.
Okay.
Now the powers must be same. Input power should be equal to output power. So what I can say is V in times input current,
That is I average.
which is nothing but d times IL,
IL.
is V naught times IO.
I.
Okay, IO, V naught times IO. Now IO is nothing but ID, and ID is nothing but 1 minus d IL.
IL.
Okay, so what we have done is we have established the relation. So okay, let me put it this way. So what you have is you have some resistance, load resistance here, right? R. We are talking about CCM throughout. So the output voltage is constant. So if the output voltage is constant for this resistance R, this resistance will then dictate the load power, right?
Yes.
So power output is V output squared by R. That is equal to V in D times IL.
Okay.
So the average of IL, that depends on the load. So if this is the inductor current, the average will depend on the load. If you increase the value of the inductor current will become like this. If you reduce the value of inductor, the inductor current will become like this. But the average will always be here for a given load. So this is how we find out the average value of B. Now if from the average value of inductor current you can find out the average value of B also.
Okay. So that is again that relationship Li is equal to.
But when you are talking about non-isolated DC-DC converters, I do not think you have to talk about flux. But flux is really required. Means I'm not saying it is necessary, but it is very useful tool when you are studying about flyback converters.
Flux that time it is very necessary
That
because
is
that.
because now that is the only thing that is linking
Yes, yes.
this primary and secondary.
And
We will
then
discuss it next week.
again, the maximum Bmax, we have to take care of that Bmax.
Yes, now the rest of the thing comes from the inductor circuit design. The inductor design comes from this only. So if you are going for a low frequency or maybe a low value of inductor, that means you are forcing the beep to be very large. So anyway, your inductor circuit will be very bulky. Inductor will be very bulky because you have to accommodate that much of flux. I should not say your B is going to be very large. Your flux is going to be very large, and if you have to keep B at your desired value, maybe at the knee, then you have to have a larger magnetic circuit, a larger core of the inductor. That is why with reducing frequency, inductor size increases.
Okay. But again, sir will discuss that magnetics part in the design of flyback transformer design.
I think so. Actually, there are two ways of explaining flyback converter. One way that I like is using the flux because that gives you the practical uh, scenario of what is actually happening. Another way that is similar is to use the magnetic circuit of the transformer. That is, the equivalent circuit of the transformer. That is, this was a practical transformer. Now you consider the magnetizing inductance here and consider this as an ideal transformer. So in that case, you can say that the current through the LM is like this. So basically, magnetizing current or flux, they are the same thing. This is
Here,
understandable, right? Because in a transformer, we know that the flux density does not change with load.
no,
Whatever flux is there in no load, that much flux is there in full load.
but that is in transformer. But in coupled inductor, actually the load will decide everything.
Load will
Because
decide what?
load will decide how much the primary current is going to flow, and that is in the off period.
Yes, in this
That's
case, yes. Hmm.
That is the difference between the
Yes.
coupled inductor and a transformer.
Hmm.
Regular transformer, when the power
No,
flow is
why I was saying this is, um, in this case, the operation is like this. When your switch is on, when the switch is closed, then this ideal part of the transformer is not working at all.
not at all, not at
The whole current is flowing through this magnetizing inductance, and this current is increasing.
all. And that current is getting reflected when the switch is off.
Yes, and when you are turning it off, this current, as inductor current cannot stop, it is flowing like this,
It is
and
secondary.
that is reflected here.
Yes.
It is inducing a voltage like this in the secondary because it is dropping, right? So dot terminal will now have plus, it will have minus. So that is reflected like this, undot plus is minus, and this diode will start conducting when you open the switch.
That is why resetting is not necessary in the flyback.
What is not necessary?
Resetting the core
Yes.
is not.
Yes.
Okay, thank you, sir. We will calculate according to the N5 is equal to Li.
Hmm.
You can have the average value of plus.
So basically, if for any DC-DC converter, or at least these three I can say, the inductor current, the ripple, that is dictated by your design. How much frequency you are using, how much inductor value you are giving, but the average value, that is dictated by the load. You have no control on it. Because if you look in case of a buck converter, that is easier to understand. Buck converter output looks like this. So whatever the load current average is, that much is the inductor current average.
Yes.
So we have no control on the average value of it. What you have control on is the peak values, how much you want to keep. In that way, you have to design the inductor for a given frequency.
Sir,
Yeah.
sir, you are discussing this flyback converter.
Hmm.
Sir, in this, the actual energy transfer happen only when the switch is off. Is it, sir?
Hmm.
Okay. Whereas in forward converter, the energy transfer is happening when the switch is on.
Yes.
Okay. That is why flyback converter doesn't need flux reset.
Yes. So whatever flux you get inside, that much you give out.
Okay.
That or whatever energy is stored, that much.
Sir, there is.
No, just a minute.
Okay.
Can I give it more than 50%? Okay, I will discuss this next day. Okay, it will take some time to reset. Right now, you do not take my word.
But if we had to restrict the D, it should be below 0.5. Then only that reset will happen.
Yes, D is 0 below 0.5 means definitely that will not happen, but that would depend on this also. I have to look at it once. I cannot recall.
Sir, you were saying about this flux BH curve. You have drawn the BH curve here and said that you are operating at, if you are operating at the knee point. No, sir. It is below. Yeah, this curve, this small red one.
Okay, whatever. I will draw it once again. Just tell me. Tell me.
No, sir. This BH curve. If you are operating at knee point. Sir, you were saying something about it that that's why when the frequency of the inductor decreases, the size increases.
What I am saying is, suppose for a given frequency you have the inductor current like this. Okay.
Yes,
now, keeping the load same, you reduce the frequency, and the circuit does not go to DCM. Okay. Does not go to DCM. You have that much of room. Now, what will happen is, with reducing frequency, your current ripples will increase.
For
It will
reducing the
become like
frequency, it
this.
will increase. Okay.
Current ripple will increase means your flux will also increase like this. Right?
Flux in the core.
Flux
Yes.
in the core, that will start increasing like this. So you have to have enough room for the flux if you do not want the B value to overshoot this.
Okay.
So to have enough room for the flux, you need thicker core.
Okay. The core we are selecting should be linear for a more extended period.
Core cannot be linear or non-linear. It's about the material of the core.
Yes. The material. Yes, sir. It should be the more than the knee point. Also, it should be linear for some time.
No.
Some
Cores that
region.
you will get in the market are ferrite. Could you please mute yourself, others?
Yes.
Yeah. So the cores that we'll get to buy in the market are mostly ferrite cores. There are other materials for advanced high frequency applications. I don't know much about them also. So the ferrite core that has more or less, you can say, a 0.2 or 0.3 Tesla, somewhere like something like this. So you will want the operation to be such that it never crosses this value. What if it?
Yeah,
Okay.
you're saying by keeping the load constant, if you increase the frequency, there has to be
Reduce
sufficient room
reduce
in
the
the core.
frequency.
Yes, reducing it. Yes.
Means
It
you
is.
are having more ripple on the current.
Yes,
Average
sir.
is still the same.
That is
You,
disabled the load.
yes. So more. So the phi max now increases. So you have to give enough room for the phi max to flow. Previously it was flowing through this, some A1. So you had phi max 1 by A1, your B. You do not want this B to increase. So now you need, it is not square, okay, it is 2. So
Okay,
you have
sir.
to increase 2 A so that you can get the same B.
Oh, okay, okay.
This is the cross section area of the core. Core is like this.
Yes, yes.
Again, do not get wrong impression that the core is hollow. I am just drawing 2 cores.
Yeah, yeah, yeah. They are different. Okay.
Cores are solid. Okay, anything else? I'm sure we will not be able to cover the questions. I will see if there is any interesting question. Anyway, questions will be covered tomorrow's session. Jitendra will do. This thing we covered, right? What is the primary effect of increasing inductor value in DC-DC converter? Our current triple will come down. So we can go with a smaller capacitor. Okay, one last thing we will discuss about this circuit and then we will stop for today. This is a boost converter. Output voltage variation of the converter with respect to input voltage is given by this. The graph of FD versus D. So what they want us to find out is V output by V input versus D. So the voltage gain versus D. For boost converter it's minimum 1, and this thing says that as we keep on increasing D, our voltage keeps increasing. And reaches infinite. So what does it mean? We will get infinite voltage from a boost converter if we keep on increasing D. Actually, in reality, there are non-idealities. There are resistances here, 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 like this, and they will restrict this increment. So in reality, we get something like this. Looks like an induction motor curve. Anyway, in reality, we get something like this.
Sir, typically at what point of D we will get the peak?
I think somewhere around 0.6, 0.7. Generally, boost converter, to have a good efficiency, this gain is restricted within 2 or 2.5, maybe, hardly. That also sounds very large. If you want a higher boost, you have to go for isolated converters.
Okay, okay. That 2 or 2.5 occurs well within 0.6.
More or less. You see now how much it gives at 0.6. 1 by 1 minus 0.6. It gives 2.5.
Yes.
If you want larger gain, you have to go for isolated converters, because there you have transformers. With the transformer turns ratio, you can have boost.
Sir,
Go ahead.
In flyback, can we operate the flyback in more than 0.5 duty cycle so that it can have the boost phenomena more prominent?
I think yes, we can, because flyback is nothing but an isolated buck boost. this is given by N2 by N1
Hmm.
times D by 1 minus D. But I cannot exactly remember the saturation case. So what happens? It'll take me some time to do that. If I have like this, okay. So when I am turning it on, then on state what is happening is V1 is input voltage and V2 is 0. If I consider the magnetizing inductance to be Lm, then V in equals Lm di by dt. So whatever delta I you have is V in delta T by Lm. Okay, and psi is Li. So delta psi is V in delta T by V in delta T. Okay. So delta phi
L.
N. This, so whatever the increase is there in on time, that much is the drop in the off time. It happens. Then what happens in a forward converter? You see, in forward converter, when you open this switch, sorry, when you close this switch, the current flows in the magnetizing inductance also. In this also, the current that flows here, that gets reflected here, and that supplies the load current. Okay, now when we are opening this, the current stops here, the current stops here, like an ideal transformer, but the current that was flowing in the magnetizing inductance, that has no path to flow. It cannot flow through this inductor because this is an ideal transformer. So if it flows through this, there should be a reflected current here also, but the diodes would restrict that. So for that we need another reset circuitry like this, not here, before the switch, so that the power get transmitted back to the source. Am I drawing it correctly?
The resistance will be there, sir, in series with the diode.
Not necessary.
No, not resistance. In fact, it is better to avoid resistance. When you have the source, you can give the power back to the source. So why waste it in resistance?
You want to make deliberate
No, this sir, this
crossing.
diode inductor is flux reset.
Hmm.
Yes.
Okay. Then it is lossless core reset, something like that. I don't know.
No.
Actually,
Lossless core.
they have some resistance on the. Okay, sir. Let's see.
No, that much we can. We're not talking about loss in the core. We're talking about the stored energy in the core. We have to
Yes,
give
sir.
it some path to go back.
Yeah. So that's why it will dissipate it with the L by R time constant if there is a resistance
Do not
introduced
say
to the diode.
dissipated. It is given back to the source.
Ah. Okay. Sir, what? Sir.
Yeah.
Sir.
Go ahead.
Sir, you are saying this energy in the inductor is given back to the source. Sir, in source, what form it gets reflected? Which parameter if we measure, we can see that the energy is coming from the inductor to source.
Uh,
Current is
okay. Uh, Parameter means if you see. So what is happening is this is flowing. This current is flowing like this, and just like an ideal transformer, that is being reflected here in turns ratio,
Okay.
and here is the source. It is going back to the source like this.
Hmm.
So the source, you can see that source is positive negative here, and the current is flowing like this.
Hmm. Yes.
okay, sir. We'll discuss this further.
Sorry.
So, sir, with the current direction, we can only with the current direction we can say.
Yes,
Oh,
we can say that the power is being fed back to the source.
Sir,
Yes.
sir, I have one small doubt in current regulator circuit, sir. Current limiting circuit.
Current limiting circuit.
Yes, sir. In a voltage regulator.
Mm,
That's in a previous
yeah, go ahead.
assignment question, sir.
Hmm.
Question number 3. Assignment 6, question number 3.
Wait. This thing we think we are discussing sometime back also, right?
Sir, one small doubt, not in the solution, sir, in the circuit.
Yeah,
Have
go
you
ahead.
taken? Sir, the current flowing through Q1, the collector current flowing through Q1 transistor
Hmm.
uh, is I naught, sir. Is it I naught?
I not output current.
Yes, sir.
This current you can say more or less this current you can ignore. This is one.
The current flowing through RS is I naught.
What about this?
Through R1 and R2 is negligible. It's considered negligible current.
That you can neglect, but about this I'm thinking about.
Yes, sir. That's because in all the design, the current flowing through RS is taken as I naught.
I think that happens at steady state because the current limiting does not mm, happen. That is kind of a correctional behavior, right?
The short circuit current.
Hmm. Otherwise, when it is operating at steady state, what is happening? This kind of flow. If you increase this current, if you increase this current, then this voltage drops. This voltage drops means You have larger CE. No, I'm not sure.
Okay.
If this is flowing here, I have to look into it. Okay.
Could you please look and tell in the next class,
Okay,
sir?
next class I will tell you.
Okay. Okay. Thank you, sir.
Yep.
Thank you, sir. Good night.
Yeah, good night.
Thank you.